Okay, so next I want to introduce another theorem that's also relating to connected set. And before we start proving, I assume that you guys already know this corollary. If A is connected, which implies closure of A is also connected. So I'm gonna go through the proof for this again, but right now I'm gonna just go ahead and start with the new theorem about.
Oh, let's see. Alright, XD is a metric space. Okay, A is a subset of X is connected, and A is a subset of B is a subset of closure of A, then B is connected. Proof. Okay, so how are we gonna start this? Okay, so in this theorem is also related to connected set, so maybe we have to prove by contradiction also, I think. So let's see here. Prove by contradiction. Okay, assume B is disconnected. So there exists two open set. Okay, G1 and G2, such that this is two open set G1 and G2 such that G1 intersection G2 is an empty set. Okay, B subset of G1 union G2, and B intersection G1 not an empty set, and B intersection G2 is not empty set. Okay, so this is just a definition of disconnectedness set. We already go through before. Okay. So B contained in G1 and G2. Okay, and A contained in B. So let's put it here. Just put a sin A contained in B. So A must be contained in G1 union G2, right? That makes sense. Okay, so what we need to prove, we need to prove that something that contradicts to this concept, this definition right here. So first we assume that B is disconnected. We can prove that if B is disconnected, then A is disconnected. So that is contradiction, right? Then we get the proof done. Okay, so what we have to do right now is we have to prove we need to prove A is disconnected. So if A meets three requirements, the requirement that are the same for B, then A must be disconnected. Okay, so first requirement we already have here. This is our first requirement. Okay, so let me fix the camera a little bit here. Oh, let's go this way. Oh, okay, so this is our first requirement we already met. Okay, so the second requirement, we need to prove A oh, the first requirement here we already met. Okay, and the second requirement I already have here. So we need to prove that if A intersection need to prove A intersection G1 not empty set and A intersection G2 not empty set, then we have A is a disconnected set, right? So okay, let's see. Okay, so how are we gonna prove A in G1 is not empty set here? Okay. All right. Okay, so we know we started from here. So we know that G1 is an open set and B is a subset of an open set. So let X belong to B, subset, and B is a subset of G1, right? And this one is open. Okay, so we're gonna have to go back to the definition of an open set. An open set is a set A is called an open set if all the member in A contain a ball or contain a epsilon neighborhood, and that epsilon neighborhood must be contained in that set. Okay, so X belong to that open set, so it means that for all epsilon greater than 0 there's an epsilon neighborhood of X such that neighborhood, I'm gonna just notate it as n sub epsilon of X contained in G1. Okay, sometimes we use an open ball or an open disk. Okay, so in this theorem I just go ahead and use the epsilon neighborhood because this term is used by many people, many students. Okay, if you read some other book, they use the epsilon. There's a system open ball, the same with the same diameter, but the diameter is the epsilon. Okay. Okay, so since X belong to B and B is subset of closure of A, right? Okay, B is subset of closure of A, so X must be belong to closure of A. Okay, so if we remember the definition of closure of A, what we have here, there's also the exists an epsilon neighborhood of X such that n epsilon X, okay, n epsilon X intersection A is not an empty set. This is the definition of closure of A. Okay. All right. So what next here? So if epsilon neighborhood intersect A and not an empty set, it means that there's some member inside, right? There's some member shared by two set over here. So let's call Y belong to n sub epsilon of X intersect A. Okay. Okay, so this is implied Y belong to n sub epsilon of X, and epsilon of X contain G1. Okay, so it means that Y must be belong to G1. And over here, what we have here? Over here, we can have the y contained in A. So if y contained in A and y contained G1, so y must be contained in A intersection G1, right? Okay. Let me just move up here. If y contain over here, y belong to epsilon neighborhood intersecting A, so y contain in A, and over here y contain in G1, so we have y contain in A intersection of A and G1. So this is imply that A intersection of A and G1 is not an empty set. Aha, okay. So right here, we need to prove A intersection G1 is not an empty set, and that's what we have over here. So similarly, we also have A intersection G2 is not an empty set. So we have one requirement, two requirement, and this is the third requirement. So we can conclude. So hence, so let's just put that. So if A is disconnected, right? So it contradicts to A is connected. So contradiction. So we done the proof. Okay. I think this is a very good proof. You know, this all relating to the definition of a disconnected and connected set. So next time I'm gonna prove a few more, so that you guys memorize all this definition and how we start the proof and how we do the proof by contradiction. Okay, thank you. Bye bye.